Okay, so these first two are a bit more for one material, and the last two are a bit more for two. Now the first one, you can't really write in terms of for two material, as far as I can think of. For the second one in kind of that first block, I know they're all labeled one. You can, and that's because on the first one you have not only a specific order but a specific color, and the colors have different amounts of all that jazz. Anyway, so for the first one, if you need a red ball first, so you have 5 choices for red balls, and then 2 green balls, well, you start with 7 of them, so you have 7 choices for the second, but then only 6 for the third. And then you have to finish with a yellow one, so you have 2 choices for that. So 5 times 7 times 6 times 2 is 420. For the other one, how many ways can you pull out 4 balls? Well, if you want to think about it in terms of like 4-1 material, you can essentially say, well, there's 5, 6, 7, so there's 14 balls total. And since you don't care about the order or the color, you're just going to do 14 choices for the first, 13 choices for the second, 12 choices for the third, 11 choices for the fourth, which is 24,024. This one, since again the colors and the order doesn't matter, you're essentially taking 14 choose 4. So 14 choose 4, or 14 choose 4 is 14 factorial over 14 minus 4 factorial.
So did you use 14 over 10 factorial?
Yeah. Why is my brain not working? Maybe I was wrong and you can't write that. Well, you can write it in terms of factorials. You could write it as 14 factorial over 10 factorial. But that doesn't turn into a choose situation. Probably because of the way I phrased it. So this is what I was going for. The phrasing there was poor. If I wanted to put it into a choose situation, I would have had to phrase it slightly differently. That's what I was going for, though. Out of the 14, you're just choosing 4 of them randomly. Well, for these last two, these are your arrangements and your selections. So essentially, the 5K, there has 10 people in it, and it essentially awards the first 4 people. In the first case, the order does matter because the prizes are different. And in the second one, the order doesn't matter. So essentially, the first one turns out to be a permutation, an arrangement, because the order matters. So we have essentially 10. Again, there's no nice way to read that one. 10 permute 4. That's not how you actually read it. So that'll be our 10 factorial over 10 minus 4 factorial. So 10 factorial over 6 factorial. So it breaks down into 10 times 9 times 8 times 7 if you want to. You don't have to write that out, but 5,040 ways to do that. That's why my phrasing was off in the last one. What I was technically going for was of any color. But anyway. And this one here is our choose situation because the order doesn't matter. So, you know, Alice, Bob, Cindy, Joe is the same as Joe, Cindy, Bob, Alice. So here, this is when we have 10 factorial. It kind of starts out the exact same. Whoops, that factorial is in the wrong spot in that top one. Should be on the outside of that parenthesis. But then remember, essentially with these, we have to essentially take out the ones that we're over counting since the order doesn't matter here. Since there are 4 things that we're choosing, the way to write 4 things in different orders is essentially 4 factorial. So we need to divide back out by that many. So essentially this turns into 10 times 9 times 8 times 7 over 4 factorial, which, well, okay, if I'm expanding that out, let's do 4 times 3 times 2 times 1. Again, this is for the quiz. I do want you to write the factorial notation. You don't have to write the simplified version, but at least give me the factorial. What numbers does this turn out to be? 4 times 3 times 2 times 1. This way, there's only 210 ways to do it. If I calculate that right. 9 to, yeah.
So like the third one would be like an arrangement, and the fourth one would be like a selection.
Yeah, so the first 5K question is an arrangement, and the second 5K question is a selection. Yeah, exactly. Oh, sorry, what happened? Oh, so essentially we have 10 factorial over 6 factorial, 4 factorial. So I essentially canceled out some of the terms between the 10 factorial and the 6 factorial because it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times, whoops, 3 times 2 times 1. I'm not going to write those out because I'm lazy. But this essentially 6 down to 1, I'm canceling out with the 6 factorial. So I'm just getting that, oh, it's lagging. So I'm just getting the 10 times 9 times 8 times 7 over 4 factorial on the bottom. Yeah. In just a second, Sam. Cool. So yeah, I didn't explain that very well, but that's what happened. Back up in the first one. So it's because of the fact, whoops, because of the fact that we have to pull 2 green balls in succession. So the first choice, we only have 5 red balls, so we have 5 choices for that one. But then when we get to having to pull the green balls out, we start with 7 green balls, so I have a choice of 7. But then I have to pull a second one out. Well, if I've already pulled one out, I probably should have also listed that you're not putting them back in. If I've pulled one out, you now only have 6 green balls left to choose from, so that's where the 6 is coming from. It's essentially the second green ball. And just to go a step further, the 2 is coming from the amount of yellow balls. So that's where the 6 came from. We started with 7 balls, we pulled one out, then we only have 6 left to choose from. Yep. Any more questions on those? That's what your quiz will be like. Probably the nicest looking quiz we've had in a while. Yeah. Did you need me to say anything about it, or you just wanted to look at it? I'll just leave it up. If you have a question, let me know. 4, pretty much kind of same format like this. 2 of them that you can kind of do in more 4-1 notation, and then 2 of them that you'll do in the factorial notation. Oh, it's freezing? Okay. Yeah, and for some reason the desktop in front of my face isn't on today, so I might not notice as much as that it's freezing, but I'll try to. So if it's freezing, yell at me, because I don't see anything. Okay. Couple more seconds. So we've got to finish for 2. It's just like one tiny little topic left, but it's very notation hefty, so it'll be a ball. And then we're gonna start 4-3. I don't know if we'll finish 4-3 today. It's not that long, but we should finish it on Tuesday, and that's gonna be where we stop for your exam on 4-3. I've been working on putting together the review packet. It's kind of almost done, so that should definitely be out on Blackboard tomorrow. So then we'll finish content on Tuesday. Probably have a bit of time to spend for potential questions or anything like that. And then your exam will be on Thursday, and then we've got 2 classes after that, and then the semester's over. So, all right, 4, 2. Now, if you're trying to take notes by hand, I suggest just sitting back for this one, because we were gonna do this by hand, and then I went, nah, that's gonna take way too much time. I'm just gonna write it out, and we're gonna talk about it. So we do need to spend some time staring at this a little bit. So now what's happening here is one of the things that we use this kind of choose thing for is something called the binomial theorem. So say we wanted to expand out this 2x minus 5 to the 4th, and remember that you can't just distribute that 4th power. People really like to do that, and that makes me cry at night, so don't do it. So essentially this is the work to expand it out, but not in the notation that you're used to. We're not actually going to simplify it. We're going to keep it generic until the very end, and then it's going to pull out something that's fancy. So I'm trying to color code it a little bit, and when it gets to the things that kind of matter, I make it different lines in case people can't see the colors. But if we were going to distribute kind of those back to, kind of FOIL those back to 2x minus 5, the 2x goes to both terms. So that gives me my first 2 terms in that expansion. And then the -5 goes to both terms. So that gives me the last 2 in that expansion. And then notice that those 2 middle terms are both 2x times -5. So I end up with 2x times -5s. And then I just rewrite that as 2x squared and -5 squared. And then we just keep doing the same thing. That 2x is going to go to each term in that, and the -5 is going to go to each term in that new expansion. So that's why these are in purple. And I know the Teams people can't see things. I'm pointing to things on a screen. But and the -5 goes to each term. Okay? I know it's a lot to stare at. There's a lot of general notation. But it's just doing exactly what you know to do. It's just not simplifying them. So these first and last terms in all of the expansions never really simplify anywhere. They just, well, shall I say, they don't combine together with anything in the middle. They just stay themselves. So this will become -5 cubed and then 2x cubed in the front. Here in the middle is where things get a little sketchy now. But notice we have the thing underlined in blue has 2 2x's and 1 -5 and a 2, and the other thing that's underlined in blue has 2 2x's because it's 2x squared and a -5. Thanks. Yeah, so Brennan, it's essentially just distributing multiple times until you get to the end. Is there a way to simplify that? That's kind of what we're getting at. It's just that I want to expand it out fully in the fully gross expansion way before I show you the way that it can not do this. So essentially the things that are underlined in blue have the same kind of terms, and there's 2 of them here and 1 of them in the second part. So they combine together to be 3 2x's and a -5. And then the ones that I scribble under in green are terms that essentially have 1 2x and 2 -5s. And there's essentially 2 sets of them here in the back and 2 sets of them in the first squiggle. So there's 3 of them that have 2x and a 5x squared. Savvy so far? I know it's a little bit to keep track of, but and then you do it again because we still have this very last one we need to distribute. So that 2x needs to go to every single term in there, and so does the -5. So that first chunk, first 4 terms are distributing the 2x, and these last 4 terms are distributing the -5. Again, the very first term and the very last term have either just 2x's or just -5, so they just kind of simplify down themselves. And then in the middle, we have some situations where I'm underlining the ones that essentially have 3 2x's and 1 -5. 3 2x's, 1 -5. There's 1 set of them in the back, 3 sets of them in the front, so there's 4 total. The ones that are kind of, you know, whatever you'd call that line in yellow with the little triangle ones, got two 2x's and two 2x's and two -5s. Same thing back here. There's 3 from that piece and 3 from that one. So you combine together, there's 6 of them. Similarly with the squiggle with the green, there's 3 back here that have 3 -5s and 1 2x. 3 -5s, 1 2x. There's 4 of those. Okay. So I know that's like a super hot mess that's written up there right now. It's the process that we all know and maybe love, but we're just not simplifying along the way. So notice, well, not really notice, I'm going to just tell you to look at it. So essentially the very last coefficients that I get when I expand this out are, now technically I didn't write down a 1, but there's a 1 in the front, right? And a 1 in the back. So the coefficients are 1, 4, 6, 4, 1. Notice a couple things. Notice, one, that it's kind of mirrored, if you will. 1, 4, then 6, but then 4, 1 again. That's not a coincidence. That essentially always happens when we expand things out in this way. But also, and I wouldn't expect you to know that this is where they come from, but if we calculate 4, 2, 0, it's 1. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4. And whoops. 4 choose 1 is 1. Now, I'm going to scroll back down in a second. Where's that 4 coming from? That was the original power of the thing that I was expanding out. So essentially, if I take the power that I'm expanding this out to, and essentially find all of the choose things, it gives me my coefficients. Now also notice that there's kind of a pattern going on with the things behind the coefficients. First, it's 2x to the 4th, and then it's 2x cubed and 2x squared and 2x and then 2x to the 0, essentially, because there's none of them. Well, the other way, it kind of goes backwards. There's no -5, and then there's 1 -5, 2 -5s, 3 -5s, and 4 -5s. That's also not a coincidence. That's kind of how it works. So essentially, I didn't mean to erase that one. So essentially, we have this kind of relationship between these kind of choose calculations and being able to expand out these binomials. So we have something called the binomial theorem. I think I can scroll down. So let j and k be non-negative integers such that j plus k equals n. Sorry? Oh, sorry, maybe I erased by accident. Sorry, that should have been 4 choose 4. So n is still the power that we're distributing this out to. So essentially you're choosing two numbers that add to that power. The coefficient of the a to the j, b to the kth term. I'll explain that out a bit more in a second. In that expansion is going to be essentially n choose k. So leave that up for like 5 more seconds. Let me scroll back up for a second. So this came from the expansion of 2x minus 5 to the 4th. Now we always want to look at this for the binomial theorem as something plus something else. So I'd actually have to view this as 2x plus -5 to the 4th. So essentially this is my a and this is my b. And notice, kind of as I already kind of pointed out, but maybe not in this much generality, that the powers on the -2 and the -5 always add to 4. So in that very first term, there is no -5. It essentially has a power of 0 on it. 4 plus 0 is 1. And then I have 3. Ooh, that was not what I wanted to choose. And then I have a power of 3 and a power of 1, which adds to 4. A power of 2 and a power of 2, which adds to 4. A power of 1 and a power of 3, which adds to 4. And a power of 4 and technically a power of 0 that adds to 4. So that's kind of what it was saying with the A to the J, B to the K, where J plus K equals N. Those powers are going to add to whatever exponent you were trying to expand this out to. Told you it was notation heavy. So let me try to clean that back up again. Oh, man. I'll leave that in there as a side note. So essentially, the thing that we're choosing is always the power of the second term. So the power of the -5 in the first term was 0, so we were doing 4 choose 0. And then it was -5 to the first, so we were doing 4 choose 1, and so on. Okay? So in general, the binomial theorem gives us that we can essentially take any a plus b to the n and expand it out. And we'd essentially take a to the n, b to the 0, and then kind of go downwards for the power of a and upwards for the power of b. And our coefficients are going to be n choose 0, n choose 1, n choose 2, the power of the second thing, all the way up to whenever you're done. So you go n choose k minus 1, no, choose k for some middle term, and then n choose n for the last piece. For this reason, n choose k is often called the binomial coefficient. So say we wanted to expand out that same thing we were already working with, but now let's do it using this binomial theorem and see if it seems even the tiniest bit faster. Simplifying it down to the very end is still kind of tedious, but let's see what the binomial theorem would get us here. So essentially our n is 4, our a is 2x, and our b is -5. So if I wanted to expand this out, and I'm kind of going to try to forget the thing that I saw on the other page that you'll probably don't have in your brain anyway, which is fine. So essentially what we want to do, what I'm going to do first is I'm going to find these terms first, and then we'll deal with the coefficients at the end. So I need to start with a to the n, so essentially 2x to the 4th. And again, I'm missing the coefficient in the front. I'm going to come back to that in a minute. And then we take that power and we reduce it by 1, and we add in 1 of the b's. And then we essentially keep bringing the power of the a term down and the power of the b term up until we reach 4 for the b term. So 2x squared, -5 squared, coefficient I'm coming back to in a second, 2x to the first, -5 cubed. I should have written smaller. And then coefficient I'm coming back to in a second, -5 to the 4th. If you want to write out the things to the 0th power, that helps you out as well, because this technically has a -5 to the 0, and this technically has a 2x to the 0 in it. Anything to the 0th power is 1. So now we need to fill in our coefficients. Well, that's always n choose something. So our n is 4, and we're going to start by choosing 0, and then essentially go up until we're choosing 4. So 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Remember, you can technically type those chooses into a calculator. So if you wanted to actually start simplifying this out, you can just grab a calculator and help you out. So if I finish expanding this all the way down to something that we can actually look at in terms of a full polynomial, 4 choose 0 is going to be 1. 2x to the fourth. Now, since there's no addition in there, I can actually distribute that power. So 2 to the fourth is 16, and x to the fourth. 4 choose 1 is 4. 2x cubed I can distribute, so we'll get 8x cubed times -5. 4 choose 2, if I want to write it out fully once, is essentially 4 factorial over 2 factorial times 2 factorial, which gives us 6. 2x squared will be 4x squared. -5 squared is 25. 4 choose 3 is 4. 2x to the first is 2x. -5 cubed is -125. And I actually don't know what -5 to the fourth is on the top of my head. 620, yeah. 4 choose 4 is 1. -5 to the fourth is 625. So we'll get 16x to the fourth. Sorry, minus because of the -5. 160x cubed minus 1000. Nope. Sorry, skipped the term. Plus 600x squared minus 1000x plus 625. Ooh, so essentially when distributing exponents, if you have addition or subtraction, that is not able to just be distributed. So that's a big no-no. We have to do, expanding out all this hoopla. But if you have either multiplication or division, then you can essentially distribute it to both terms. Hopefully that's what you meant by the rules for distributing exponents. Essentially, it can distribute through multiplication and division, but not through addition or subtraction. Like it's doing a sum more with itself. Anyway. So I know that still seems semi-tedious, but expanding this out and actually, even when you're simplifying the things along the way, if you can just follow the pattern of the binomial theorem, once you get used to it a little bit, it does actually save you a little bit of time. I believe for your homework, I think there's like 1 or 2 questions where it says something like, what is the coefficient of the whatever term? So it would say something like, let me try to think of one off the top of my head. This is dangerous. But what is the coefficient for the, let's say, x to the 7th term in the expansion of x plus 2 to the 10th. I don't know. I think this is usually how they phrase them in your homework. So essentially what you would need to recognize here is essentially if you're in the x to the 7th term, you'd be at the 2 to the 3rd piece, because remember those 2 have to add up to 10. And essentially, so we're going to 10, and the choose thing is always the exponent on the 2nd term. So our coefficient in the front will be whatever 10 choose 3 is, which would be 10 10 choose 3 is 120. So now I do want to be clear also, it's looking for 120. I know there's the 2 cubed in the back and you could cube that and multiply it by the 120. It's looking for the actual 120. What's the coefficient in the binomial expansion of it? But essentially you can do that by finding essentially what term you're looking at, and whatever the power on the B term is the thing that you need to choose out of the total amount. Does that make any sense? Questions, concerns on that? Now that I've killed your brain with lots of numbers and notation and scary looking things. Okay. So I'm really trying to remember what, I think there's only like 2 questions on the homework that have to do with the binomial theorem, and I think they're both phrased like that. When it comes to the binomial theorem and your exam coming up, I'm not going to ask you to expand it out fully. I would probably ask you something like this. What is the coefficient of a specific term? Because expanding it out fully is always obnoxious. I do understand that. All right. So there are no questions on that. We're moving on over to 4.3. So 4.3 it's called counting with functions. So we've got to kind of recall some definitions from when we talked about functions back in chapter 3, 2, 3? I don't remember. Anyway, when we talked about functions, we talked about one-to-one, onto, well-defined, all that jazz. It's going to come back to us a little bit here. Oh, it says it right there. Recall from section 2.3. That function is one-to-one. Correspondence if it is both one-to-one and onto. The function was one-to-one. It was that no 2 inputs map to the same output. Now note that in general, 2 inputs can go to the same output, but for it to be one-to-one, essentially every output can only be mapped to once. And if it's onto, that essentially meant that every element in the codomain is mapped to. So remember, there was a codomain and a range. And essentially, in the codomain was essentially all of the options you had to choose from for your outputs. And then the range didn't necessarily need to hit them all. So we have a couple of theorems that we have to talk about first. So let the cardinality of X, so remember that just means the amount of elements in that set, be M, and the amount of elements in Y be N, and let there be some function from X to Y that is one-to-one. Then we're going to have that M is less than or equal to N. Why does that make sense? So essentially, if we think about what it means to be one-to-one, that would mean that no 2 different X's in X map to the same element Y in our essentially codomain set. So essentially, if no Y value gets mapped to more than once, there must be at least as many Y's as there are X's. There could be more Y's because there could be some that don't get mapped to at all, but there must be at least as many. So there must be at least as many Y's as X's. Because if there weren't as many Y's at least, then something must have mapped to a Y twice. Or sorry, 2 different things must have mapped to the same Y. So if we change from one-to-one to onto, but essentially the same exact setup. So we have some cardinality of X is M, cardinality of Y is N, and there's a function between X and Y. But say the function is onto now, well then it must be the case that M is greater than or equal to N. Why does that make sense? So remember, onto essentially means that every element of Y got mapped to. So essentially there must be more or the same amount of x's as there are y's. So since every y in that codomain has an x that maps to it, there must be at least as many x's as y's. Because also remember that x's can only go to one thing. For it to be a function, that's what it means to be a function. Every x can only go to one y. So if every y has to have an x paired to it, there must be at least as many y's as there were x's. So kind of the point is that, well, therefore, if it's a one-to-one correspondence, so it's one-to-one and it's on 2, then it must be true that those values are actually the same. Now, why the heck do we give a crap? The reason this is useful is if there's a one-to-one correspondence, and remember, one-to-one correspondence means one-to-one and onto, between x and y, then in order to count the number of elements in x, we can count the elements of y. Instead. Now, of course, this is only useful if it's easier to count the number in x than the number in, the number in y than the number in x, of course. But in some cases, it might be. Sometimes you might want to say, well, how many elements are there in x? And it seems like something that would take a really long time to figure out how to count. But maybe the elements in y are much easier to count. So if you can count the elements in y, then you know how many elements are in x. So we'll have time to do one example of that. And then well, actually, it goes on to a different topic after that. So leave this up for a couple more seconds in case someone's still writing it down. So, say we have this. A single elimination tournament. Players are paired up each round, and the winner of each round advances to the next round. The number of players in a round is odd. One player gets a bye to the next round. The tournament continues until only 2 players are left. The 2 players play the championship game to determine the winner of the tournament. Tournament. If a tournament has 270 players, how many games must be played? So we want to know how many games are going to be played. And that's, might seem like something that's, maybe you know how many games it's going to be, but it sounds like something that could be potentially difficult to count. Because you've got to pair up people and then figure out how many people don't have to play one game because there's not an amount of people and blah, 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 blah. But let's view it this way. Let's set up a function where we're going to let G be the set of games that are going to be played. And let's let L be the set of players who lose. So essentially, we're going to define some function from G onto L by saying if we let some f of G be equal to L, we're going to say L is the loser of game G. So if we can find that this function that I'm defining here is a one-to-one correspondence, then instead of counting the number of games played, I can count the number of losers. So there's a couple things we need to make sure happen. We need to make sure that this is actually a well-defined function. Is it actually a function? So essentially, does every G only have one L? Every game has one loser. And only one loser. No, there's not two losers for one game. And there's no game without a loser. So it's well defined. Well, now if we want a one-to-one correspondence, we have to say it's one-to-one and onto. So is it one-to-one? So does every loser only come from one game? Yeah, because once they lose, they're out. So this is one-to-one. Since it's single elimination, no player loses multiple games. There's no loser that came from multiple games. Is it onto? So does every element in the codomain get mapped to? So essentially, does every loser play a game? Well, yeah, the one they lost. So every loser lost a game. There's no way to have a loser without having had a game that they lost. So it's onto. Any questions about those three specifications? Okay. So essentially, F is a one-to-one correspondence. So now we can use that idea of instead of counting the number of games, we can just count the number of losers. Since it's a one-to-one correspondence, they must be the same number. Well, if you think about this, there's 270 players and one winner. So how many losers are there? Everyone but the winner. So there's 269 losers. So if there's 269 losers, there must have been 269 games. So as F is a one-to-one correspondence, the amount of elements in G, the amount of games played, is the same amount as the number of losers, which we just found to be 269. Now again, if you put your brain to it a little bit, you could probably come out to figuring out that there's 269 games. But I feel like I would get lost in it a little bit. But if we just consider how many losers there are, which is kind of easy because it's single elimination, so it's just everyone who didn't win. And since this is a one-to-one correspondence that we created, we can use that theorem to essentially say they must be the same number. Savvy? Questions, concerns about that? Okay. I think I need to push it through for you people on Blackboard. I don't think it's up yet.